Welcome back, everybody. Two videos this week. I think they'll both be somewhat short. More Venn diagrams, more reading, combinations and counting still. Right? The two principles of counting we'll see again in the next video. Let's jump right into it with Venn diagrams. Now, Venn diagrams were one of those things that, again, can be difficult for some people because it shows a pretty complete set of information. So, for example, in this 3 Venn diagram that I've shown here, I've got some sample space or a universe set. I call it S. Some textbooks will call that U, outside of everything. And then I show how 3 different sets overlap: set A, set B, and set C. And so in this Venn diagram, I can clearly see what is in set A, maybe in 1. You can also see what's in set B and in set C. See set C here. But I can also see how those sets overlap with one another. And so maybe this little almond-shaped region, that's the intersection between set A and set C. This almond-shaped region here, that's the intersection between set B and set C. This intersection here, this almond-shaped intersection, is set A and set B together. Of course, there's one region right here in the middle, which is the overlap between all 3 sets at the same time. Right? A Venn diagram tells us about all 3 sets in every single region. I was shading multiple regions at the same time, like shading an entire circle A, set A, but that was actually made up of 4 little sub-regions here. But each one of those regions tells us very specifically about its membership in all 3 of the sets. I'll give you an example. If I highlighted, let's do this one, this region, and only this little half almond subregion there, so this green region. Is this region inside of set A? Yeah, it's in the circle for A. Is it in B? I don't think so. No, not that one. And is it in set C? Yeah, it's in the circle for set C. Right? This tells me that I could label this one little piece as set A intersection set B complement. Remember, B complement means it's not in set B. Intersection set C. I know that seems a little bit weird because we're not used to seeing quite so many sets being connected together, but that's very specific information. Each one of these little subregions can be expressed with all 3, A, B, and C, in this sort of intersection connected way. And so if I needed to read some of them, say for example, where is region A complement intersection B intersection C, that means it's not inside of A, that's A complement, but it is inside of B, and it is inside of C. So outside A, inside B, inside C. I think that's this one. Let's double check that. Outside A, okay, down below, inside B, and inside C. Yeah, I think that's this region. This, I've made it the orange color. One more. Where is region A complement intersection B complement intersection C complement? Oh, okay. That's outside A, also outside B, and outside C. The only region I see, I think that's this outside region here. Pretty big compared to A, B, and C, but do you see how this region that's completely outside of all three of the circles is A complement and B complement and C complement all at the same time. Whenever you're working on the Venn diagram problems this week, right, you will usually have to fill out some sort of Venn diagram. And this is usually how I do it. I start with the most specific information first, right? Something which tells you about its membership in all three sets. And then I work outwards from there. Because as you work outwards and as you start working with information that is less and less specific about where it's at in relation to all the sets, that's when you start overlapping. Right? If I only told you about A and B, right, that's not just one of the little subregions. I'll have to start seeing, well, how do they overlap and combine, and when do I need to avoid double counting? We had that special formula for double counting. So whenever you're working on your Venn diagram problems, just remember that every little subregion is all three at the same time, but you'll very often have to start combining them together because Venn diagram word problems will not tell you specifically, right, every single number, right? 1, 2, 4, 5, 6, 7, 8, 9 different little subregions here. You won't get 9 pieces of information which apply to only one subregion at a time. You might get one which applies to all three, and then you'll start need to combine them and see how they overlap with one another. Do an example. We'll do one with a 2 Venn diagram instead of a 3 Venn diagram to make it a little bit easier. Let's see. In a survey of 181 pet owners, so I know that the number in the entire thing is 181. 69 own a dog. Let's call that set D. 69 own a dog. 90 own a cat. Let me call that set C. And 22 said they own both a dog and a cat. So that is dog intersection cat. It's both of them. And that is 22. All right, I'll go ahead and label this one dog and this one cat. Arbitrary. You could draw your Venn diagram however you wanted to. But the question asked how many owned neither a cat nor a dog. So let's see, I don't own a dog, that's D complement, and I don't own a cat, C complement. And we're trying to figure out how many is in that set. Okay, well, let's start filling out some of this information. And this Venn diagram has 2 sets in it. And so I will start with the most specific information. That is something which tells me about D and C. And it doesn't matter if it's inside or outside, as long as it tells me about both at the same time, that will tell me about one of the specific subregions. It helps me get a good starting place. And that is this piece of information here. Intersection D and C. In my picture, that is here in the middle, intersection D and C. That is 22. Notice how that piece of information applied only to that one subregion. That's the reason I could directly label it in my picture. For the other ones, it won't be quite so easy. Well, the only other piece of information that has 2 is this one that I'm looking for, so I can't do anything with that yet. Let me go out a little bit farther and look at the information which has only one of the sets in it. So the number of people who own a dog is 69. This one here. But there's 2 subregions to which that applies. It could be this subregion or this subregion in the middle. And them added together should be 69. Well, if I add these 2 numbers to be 69, that must mean that, let me take away the 22 I already have. 7, 4, must mean that the people that own a dog which do not own a cat is 47. See how those two numbers that I've labeled add together to be 69? That's what I'm talking about. And we couldn't have done that without having that 22 already in the picture. Another reason why I start with the most specific piece of information and zoom out. So that's got this one taken care of. Now let's work on the cats. 90 people own a cat, but I've already got 22 of them accounted for. So I have 90 and I've already got 22 of them. 80, 70, 68. Yeah. That makes it so every number in the cat bubble, right, the 22 and the 68 both, they add up to 90. Because the piece of information we had over here didn't tell us, are you inside of dog or are you not inside of dog? It didn't say. It was actually referring to both of them put together, which is why we couldn't have started there. Now I think I've got 90. The only other piece of information that I'm missing is exactly what we're looking for, the outside region. But that's okay, because I have the total. If the total is 181, and I've already taken into account all of these, oops. Let me subtract all of these numbers. 181 minus 47 minus 22 minus 68. 47, 22, 8. My calculator shows 44. So that must mean this number is 44. So let's debrief. The number of people which own a dog but not a cat is 47. The number of people which own both a cat and a dog, 22. The number of people which own a cat but not a dog is 68. And the number of people who own neither a cat nor a dog is 44. And if I added all four of these numbers together, it should be exactly 181. Again, it kind of makes sense because that's where I got the number from. I subtracted everything from 181. 44. In this particular problem, it just asks for that one number. Sometimes you'll have to fill out the entire diagram. Sometimes they're only going to ask for one number. Sometimes they'll ask for some other weird combination of numbers, right, where you'll have to go back in after you fill out the entire diagram and add a few different numbers together. It all depends on the way that they express the set. So again, Venn diagrams seem really hard at first, right? Especially if you haven't worked with them for a while or maybe even ever. But they're not as complicated as they seem. It's all about the information which is overlapping and the information which is not overlapping together. Okay. The other half of our video today is about counting principles. We started seeing these last week, but they're going to become more important this week. So I figure I'll talk about them in this video as well. I heard this in marketing before, so I had to go look it up today. I looked up on Sonic website. It said they have 1,063,953 particular fountain drink and slush combinations. And you see this sometimes in marketing. Oh, it's really, really flashy, really snazzy. Oh my gosh, who counted all those things, right? No one wants to sit there and count. Oh, okay, you could have Diet Coke with vanilla in it. You could have a Diet Coke with lime in it. You could have a Dr. Pepper with cherry in it. And nobody wants to count all that. And nobody did actually sit down and count them that way, right? They use these counting principles to enumerate all the different possibilities instead of having to specifically list every single one of them. Whenever you're looking at a counting problem, I'm generally looking at two principles. We saw this last week. So when we count, if you're counting things which are already fully complete, they are the things you're talking about. Say, for example, in this example about the die, if I'm counting outcomes, then I'm adding them together. But if I'm breaking apart an outcome, I'll need to multiply, counting principle 2. If I were to look at Sonic, for example, if I were counting all the different ways, that I could have, this kind of soda with this kind of flavoring in it versus this other kind of soda with this other kind of flavoring, right? Because those are complete outcomes, I would add those results together to tell me the total number of possibilities. But if I am piecing it together, saying, okay, well, if I break this down, I could have one of 8 different combinations for the base drink, and one of 6 different combinations for a syrup, and one of 4 different combinations for maybe a fruit which goes in it, right? Then I start multiplying those things together. And the trick between them is, am I allowed to sort of mix and match and have all of them or none of them? Or am I being given something which is already complete and cannot be changed anymore? It's already complete. It's probably an addition. And if I'm mixing and matching and just telling you part of the result and letting you choose, then it's probably a multiplication. So if you are considering a complete outcome at a time, generally you would add to combine. And this example with the die is a good one because it says, if 20-sided dice is rolled, how many possibilities are odd or multiples of 4? Well, these multiples of 4 or odd numbers, they're already a complete outcome. I don't need to multiply how many numbers are odd times how many numbers are multiples of 4. I just want to collect them all together. How many numbers are odd? Let's see, that's 10 out of 20. How many numbers are multiples of 4? And that'd be 4, 8, 12, 16, 20. 5 multiples of 4. And now, just like my Venn diagram, I have to consider, are there any multiples which have been counted twice? I don't think there are any numbers which are odd and multiples of 4 at the same time. All the multiples of 4 are even. If there are, you would have to subtract those out. But here I don't need to. That's 15 total combinations. 15 total combinations. Remember, that is our... We saw this as kind of a half formula before, but that was, we didn't always get this thing out as formula to memorize because it seems kind of weird to write it. And I apologize that my lowercase letter n and my intersection symbol can look somewhat similar sometimes in my handwriting. Generally, when it's directly outside parentheses like that, especially if there's nothing before it, it is talking about, that's just a lowercase n. If you want to correct, if you know that that's going to be really hard to tell apart in your handwriting, you might want to make it an uppercase n. I don't usually do that. I at least try to, I don't know. Some of the things I'll do is sometimes I'll make the tail part of the N a little bit more pronounced if I'm writing large enough. And you'll also see that at the very end, the N kind of has a little curly on it. Again, my handwriting is not always perfectly consistent there, so that's why I'm apologizing. I at least try, hopefully. But this was basically our double counting formula. Right? If you count something in one set and you count something in a different set, you have to make sure to go back and subtract the part which has been double counted. It was in both A and B. I don't think we need a big long formula to express that idea, though, which is why I don't use this formula by writing it out quite so often. And that brings us to counting principle number 2. If you build one outcome out of its components, we generally multiply to combine those things. And whenever I say building one outcome out of its components, you'll see a lot of problems on the homework like this. Like I'm choosing an outfit, and I have 6 pairs of pants and 3 shirts to choose. How many different ways can I choose one from each category? And that is, I'm picking one component and from each category, so I would need to multiply to combine those possibilities. That's the kind of thing you'll be looking for in the word problem. Smaller example, standard automobile license plates contain 1 number, 3 letters, and then 3 numbers. How many different standard license plates are possible? Assume repetitions of letters and numbers are allowed. Okay, so I'm basically making a whole bunch of components here. So there's 1 number, 3 letters, 3 numbers. How many different ways can I pick the first number? Let's see, there are 10 numbers, 0 through 9. And each one of those numbers can be followed by a letter. There are 26 letters. And there's no restrictions whatsoever about which numbers can follow which letters. It's completely free for all, right? And so if there were restrictions, I would take that into account. Say, for example, if the first number had to be followed by a vowel, A, E, I, O, or U, then this wouldn't be 26 anymore. It would be 5. Whatever restrictions are described to you in the word problem, just make sure those are accounted for in the ways that you are multiplying all of your possibilities. Here, there were no restrictions. I'm allowed to repeat the same letter twice, so I'm still 26. And I'm allowed to repeat the same letter the 3rd time, another 26. Again, that number would go down if I weren't allowed to repeat. If I couldn't repeat any letters, then there wouldn't be 26 left after the first time because I'd have to set that letter aside. The 1 number, 3 letters, followed by 3 numbers. 10 numbers, 10 numbers, 10 numbers. Oh, okay. Well, that seems like a lot. That's 26 times 26 times 26 times 10 times 10 times 10 times 10. That's pretty big. I'm going to have to ask my calculator. How many possibilities is that? Oh my goodness. My calculator shows that this is 175760000. Going back in to add commas to make this a little easier to read. 175,760,000 different combinations. You can see these numbers get really big really quickly, especially when we are multiplying. So when Sonic said up above that there were more than 1 million combinations, maybe that wasn't super impressive, right? Now that I go back and think about it, because this got really big really quickly. Another example that I like to give is whenever you go to YouTube, a YouTube video ID, that the big list of seemingly random letters and numbers at the end of the URL there, that's the video ID. You can think of that like a serial number. Every video has a serial number or a video ID, which is 11 characters long. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 characters long. And each one of them can be a letter or a number. That letter can be lowercase or uppercase, and the computer tells them apart. And there are 2 special characters after that. And so if you add all of those possibilities together, it can be a number, just 10 possibilities. It can be a letter, uppercase and lowercase, so 26 uppercase, 26 lowercase, and 2 special ones after that, 10 plus 26 plus 26 plus 2 special ones. If I remember correctly, that should be 64. And unsurprisingly, if you're a computer nerd, you may have heard something being referred to as base 64. before, that's exactly where this comes from. So I would say to you that this is a base 64 serial number, or a base 64 ID number. So every single one of the letters or numbers are one of 64. But that's 11 times. So if I wrote 64 11 times, how many possibilities is that? You might say, okay, well, one, that's a lot of possibilities. And you're right, it is. But YouTube gets a lot of videos that are uploaded. Think of how many videos are uploaded every single day. I'm going to have to ask my calculator. And because I'm really lazy when I'm typing things into my calculator, I'm going to use exponents to do this. I know exponents mean multiply by the same number over and over again. So I'm going to type this in as 64 raised to the power of 11. And boy, my calculator tells me that's a pretty big number. It's so big, it can't even tell me what that number is exactly. It has to round this off. My calculator tells me that there are 7.3789, and I'll stop giving decimals after that, times 10 to the 19th power. Oh my goodness gracious, that's a scientific notation number. What that means is this decimal has actually been moved 19 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 times total. That's a big number. That's how many videos that YouTube can actually give a unique serial number to, or it runs out of them. It's even hard for me to go count all the zeros to add the commas in the right place. I'm not even sure I'd like to give this a name. Thousands, millions, billions, trillions, quadrillions, quintillions, 73 quintillion, 786 quadrillion, 900 trillion videos. It's a huge number. You can see these numbers get very big very quickly. And it's all having to do with picking the number of possibilities and multiplying them together. Believe it or not, the addition and multiplication principles of counting are basically all we had for this video, plus the Venn diagrams in the beginning. It's a short one, I know. It's a little bit new for me. I'm going to try not to be quite so long-winded in the future, but you know me, I like to get going. Anyway, I'll see you for the next video.